Okay, I'll take that as a cue to get started. 5 past now, so I'll try and keep an eye on that time. Alrighty. Lecture 3 of calculating in EFT. Let's talk today about equations of motion or field redefinitions. We'll work through an explicit example. So if you haven't done that one you were suggested, you'll see it on the board today. And hopefully that clears up any doubts you have about it. And if we have time, we'll look at unitarity as well and what that tells us about EFTs. So let's write that down. Field redefinitions. And unitarity. Right, before we get started, a few words about last lecture. We couldn't make it through all 3 examples for, remember, our Tuhin model for EFTs is this, given by this EFT action that is a function of some complex scalar field phi. And we wrote a phi for theory plus 3 dimension 6 operators. And we claim that is general enough EFT. We'll show today that it is. And for that, we didn't show explicitly, but we looked at several different models and we saw, well, the singlet model will give us this particular operator. The Goldstone model will give us this other particular operator. And if we looked at the ADS EFT, it will give us even another one. But how do we know that it's in capturing all of the possibilities? Well, for that, we need to build a basis that is large enough and has all of those operators. But in that sense, there's also the freedom or the feature pushing the other way that field redefinitions reduces the dimension of the basis, or the number of operators. So we'll go through that today. And the key point to take away from that is that all of those coefficients, CG, CS, and C6 for these 3 operators will take different values for different models, but as long as we keep them general, we can then capture any UV model. And that is the sense in which EFTs are model independent. You just look at those terms and keep them general. It doesn't matter whether they happen to be at the high energy. You can always keep them general, do your computations, even your one-loop computations, compare with experiment, and after that, you could always set one to 0 if you want to, or the other one and say, I'm talking about this or that model. But that is the power of EFTs, that as long as you have a complete and full basis, you can describe anything, any UV model that's there. One of the UV models that got you a bit confused last time was the Goldstone boson case. In particular, I got questions about how do you actually build a full model, full renormalizable model that will give you that. So for that matter, in the notes for the lecture, I think it's the lecture that's uploaded right now, there's a problem for you guys to solve. If you give me more questions, I'll give you more problems so that you show it yourself. But there's an SU2 triplet in that case that I call delta. It's an SU2 triplet with 3 degrees of freedom that are real. And after spontaneous symmetry breaking, 2 of those will be the Goldstone that we talked about, and the other one will be the Higgs, or A Higgs, that is out of the low scale spectrum. It's heavy, so it's not there. But you can work through that example and see how explicitly that will arise in that UV complete and renormalizable model. That is very much like the standard model in that sense. Alrighty. So we start with field redefinitions. For that, it's good that Tim already talked about this. How field redefinitions leave the S matrix invariant once we define it in terms of the path integral. This is going to be a quick reminder about that. And this is section A of what we'll talk about today. And the statement is if I do a variation of phi going to phi plus a deviation, delta phi. The difference now is we're in an EFT, and that variation itself is going to be in an expansion on lambda squared. The statement is that as long as this variation delta phi is a polynomial or arbitrary degree, but that starts at 2 powers of phi with whatever coefficients, then you have that both the original and the transform field, and again, I'm keeping up with the bad practices of physics, I call both the same phi, but this, you can think of this as phi prime if you want to. But you'll see that we do this because in the end it doesn't matter. But the point is that both fields, phi and the transform phi, excite a one particle state from the vacuum. This A dagger is the creation operator that we defined earlier on, and the statement that this is the same as putting the same in between the same bracket, the transform field. Again, I think you mentioned you can check this explicitly if you break this down into creation and annihilation operators, and that'll be true if there's more powers of phi n. I'm assuming you've taken some QFT classes and you've had your fair share of commuting and anti-commuting creation and annihilation operators. So in that case, that wouldn't take too long to check. The proof, or the way to show it, is with a path integral, but in this set of lectures is about computing, so let's take an example and show it to yourselves. You can, again, it's a problem that you can carry through all the way by yourselves if you want to. But what we're going to show is that the amplitudes that come out of the original theory and out of the transform theory are the same. That's what we're shooting for, so that they're physically equivalent. What's the theory we're going to consider? Well, this theory with, I'm going to call this theory with action S. That's what we will call the first one. And to keep it simple, it will be the renormalizable part plus a new operator that we hadn't considered. You can write this as a linear combination. In fact, it will look something like the operators that Tim was talking about. But it will be a combination of one of the operators that we did consider, this del square acting on phi star phi. But if you break that down, when it acts with the second derivative, you'll pick up the second derivative of phi star of phi, but also a cross term. And I want to get rid of that, so I subtract phi star phi times the cross term, basically. Which then will simply be, and this of course has a coefficient, let me write it in here, C over lambda squared. And if you do use that expansion that I mentioned, or that let the derivative act in there, you'll get box basically acting on phi star and then phi. But the other one is just the Hermitian conjugate. Very good. So this is the theory we start with, theory S, renormalizable plus a single operator in our EFT. Now we're going to do a field redefinition just as outlined there. And we'll obtain a new theory S with action S bar. Very good. So the theory with action S bar. The two we'll compare with, and we obtain it from the old one by doing that shift. and stopping, because it's still an expansion in lambda square, so we'll throw away a number of terms. So first, the things as they were. SE, I'm calling all of these. Hopefully you're not familiar with the notation. This term in the action I'll call SE. And then the first variation of the action with respect to the field, the renormalizable one, times the variation of the field. Looking at it, the full variation of the field is delta phi over lambda squared. There would also be delta SE. By delta, I just mean the variation with respect to the field. I can make it more explicit if you like and write it like delta S delta phi. This is the functional variation. There will be this term too, at linear order, the variation of the SE action with respect to the field, and then the variation of the field itself. I'm not going to consider that one. And I want you to think why. I want you guys to think why is it okay to not consider that one. No, that's not quite the answer. It's not a question of motion. I've heard it here and there. This, I've hidden it, but SE itself has 1 over lambda in there. So this is higher order in our expansion. We can throw it away. And that's nice. Again, we'll use this over and over again. An EFT is an expansion in a parameter. It doesn't make sense to keep higher orders unless you do it everywhere. And here we're only working to order 1 over lambda squared. Right, but what that looks like explicitly, now we're going to do it, would be yes. Yes. Well, in practice, we're going to stop, well, we're going to take the phi cubed term, and then that works out with an order 1 coefficient. It will be lambda squared, the same dimensions as phi. But this is good to point it out. This itself will have an expansion on lambda, so you can also expand those terms in there. In practice, we'll get the first non-trivial one for this case, which will be phi cubed. And then you can see that the dimensions work out. Thanks for the question. Any other question? Oh, and this, by the way, this is a complex field, so we treat them separately. There's the field and its Hermitian conjugate variation as well, which is just taking the Hermitian conjugate there. Righty, so the variation in here, there will be the equation of motion for the field times the variation, which is delta phi over lambda squared, and the equation of motion that you can, I'm sure you've done this a number of times, but you can write as minus delta squared plus m squared. It's a variation with respect to phi, so it will give us phi star. And then the lambda cube term, which is minus lambda halves now of phi star. Now you can see that we can carry out our plan of getting rid of that operator that we started with. In particular, it's good to look at this line instead when it's in the form of delta phi square acting on phi star. We would also have a delta square acting on phi star in there. If I choose right that delta phi, I can cancel it out at a cost, because there will be these other terms in there as well. But What is that choice? Well, the choice is, this is green. Choice is delta phi, just 3 powers as I was saying. And it's just CE, that coefficient, so it cancels out, times phi square phi star. Right, I'm doing, hopefully, it's a bit of algebra, but hopefully you can follow the spirit, which is use that to cancel that other one. And after we've done that, what we're left with is, of course, what we've set out to do happens, that cancels out, but we also have these other 2 terms in there. One of them is going to look like lambda 5/4, and the other one like 6 fields. And I want to write this as S4 bar plus S6. Again, this notation that will be renormalizable, and a dimension 6 operator, which will look like S4 plus, I'm just collecting those terms then, before x phi square phi star over lambda square CE. The mass term is going to show up here, minus m squared phi star. And then the second one is minus lambda halves CE lambda squared, and those 6 powers of the field, or 3 of phi and 3 of phi star, plus emission conjugate. But now I stare at this long enough and I realize that this is already emission conjugate itself, so that's going to give us just a factor of 2 up front. Hope you can see that from the back. Righty, so now we ended up with a different dimension 6 operator out of this process, but also a contribution to quartic coupling in there. And if you look at this, remember what I mean by S4 with a different superindex, so any other adornation on it, is the same parameters, but with a different name. So in here, there's gonna be a lambda bar. The mass term is gonna be the same, but this lambda bar will be related to the lambda in this S4 plus that extra contribution there. I'm going to make it a bit clearer for you guys. So in here, there's going to be in the action a term that is minus lambda bar over 4 phi star phi to the 4th power, because that's just our definition of S4 with a bar on it. Every parameter gets a bar. Whereas on this side, we have S4 as we had in the beginning, and it comes with our own lambda. But that other term in there also looks like a 5/4 term. What does it have? It has a minus sign up front, minus CE m squared over lambda squared. And then the same thing. Right, I'm just collecting term. This is like harvest time. And equating left and right, I mean, we're doing over and over again, equating the 2 actions to connect them. A little bit like matching. And out of this relation, I get that lambda bar then. I'll not use that color just in case you can see it. Lambda bar will be lambda plus that extra addition, and you work out the factors up and down for, that will be 8 CE m squared over lambda squared. Questions? I see some confused faces, but. If anything is unclear, I mean, I am going through the algebra slowly so that you follow, but if that's not slow enough, let me know. And the new thing is, in our notation, there's a contribution to that S6 operator and that relation of the coefficient. If you go back to your notes, so just trust me for now, is whatever was in front of phi star phi cube, we call C6 over lambda square. So C6 over lambda square is all of that with the factor up front minus lambda CE over lambda squared. So that is just working through what we call both theories, S and S bar. And we've managed to do this field transformation, get to that other field, and connect the couplings that each action has. Now we're going to compute amplitudes, or part of amplitudes at least. But you can, I'll leave this as an exercise as in the notes, you can get to the same place if you just take the original term in the Lagrangian in here at dimension 6, and you apply on it the equations of motion. It is not so hard to guess that will be the case, because at heart what we're using, the input we're using in this field redefinition is the equation of motion as the field, the first variation of the action with respect to the field. We're putting it in there, algebra, blah, blah, blah. We end up with a different operator. If instead we use the same condition on the action, as long as we're keeping it to the same order in 1 over lambda squared, we'll get to the same result, and that's what I ask you to do in one of the problems. And that's also something that will allow you to understand a lot of the literature in EFTs when they sell a field redefinition is the same as an equation of, using the equations of motion. But we also should be aware that that is true at this order in the expansion. Of higher orders, as I was talking to you the other day, the safe procedure to use is field redefinition. If you use equations of motion, you have to modify things a bit, but you can still do it. But it's not as straightforward as with field redefinition. But to the main course of the meal today, which, yes? Yeah, you could do that. I mean, I would argue that there's a new coupling. There's this phi star phi cube in here. Well, you couldn't have introduced anything new at dimension 4 because that's the complete dimension 4 Lagrangian. Anything new at dimension 6, well, again, we're using that to redefine it, but that's the point of a complete basis, that there's nothing new happening. Yeah, but thanks for that question. Any other question? Alrighty, so now on to compute amplitude. Still have good on time. There's going to be, I don't know how good you're or how keen you're on combinatorics, but when you do Feynman diagrams with scalar fields, you're going to have to count quite a bit, and some of these might not be intuitive or straightforward for you, but hopefully I'll guide you through the steps. So now we go on to proving or showing both theories give the same amplitude. We're going to start. Which one is easier to start with? So the easiest one to start with is S bar, which I am calling the green theory. This is something that some other lecturers have done. I'm going to take just for ease, for making those symmetries and those combinatorics clear, I'm going to take all particles coming in for now. So I'm going to look at a 4-point in which scalar coming in, anti-scalar coming in, another scalar coming in, another anti-scalar coming in. You can flip any of those two to be outgoing particles. You change the sign of the momentum, and there you go. You have it. the amplitude for this in the S-bar theory, let's stare at it. So it has this renormalizable term and a dimension 6, which is 6 powers of the field. So the only term that's going to contribute to that 4-point at 3 level is the only term in the action that has 4 powers of the field, or 2 each of phi and phi star, which is this lambda bar term in here. Okay, this is, I hope you don't find this insulting. This is pretty simple, but again, I'm going to the details. A lambda phi 4 theory, that's everything that's in here. The Feynman rule for it is just putting an I out front and doing, again, those combinatorics, which would be, roughly speaking, I can associate any 2 of these incoming particles, phi's, to any of 2 of these phi fields in the action. That will give me a degeneracy of 2, and the same thing for phi star. So this will be 2 times 2 times lambda 4. Lambda bar 4, sorry, that's important. Right? And that's the whole reason why we typically put these combinatorial factors in front of lambda phi 4 theories, because we know the Feynman rule is going to have extra factors of 2. That was easy. Well, I hope that was easy for you guys. So minus I lambda bar, and it'll be useful to rewrite lambda bar in terms of the other theory ones we want to compare. That'll be lambda plus 8 m squared c over lambda squared. Alrighty, now let's do it for the other theory, what we call just S. In this case, there's 2 contributions. The first one is, again, simple enough. There's a lambda term in here that we start with in S4. But then this operator we started with is also got 4 fields in it. So this will also contribute to the 4-point in this S theory. So when we try and do the same thing, going to be 2 contributions now. The first one is going to be, again, minus I lambda. The second one is coming, we'll take it out of this form of the operator with a del square acting on field. But the idea will be the same. Now we have to put labels on these guys. So let's call this momenta P1, P2. Let me do it so that, let's make it so that even and odd are particles and antiparticles, P2, then this is P3, and this is P4. Very well. Then that extra piece is going to have, well, first of all, the coefficient that's in front of it with an I CE lambda squared. And then there's those derivatives, square acting on fields. I remind you, you can do this again. That's why I wrote the canonically quantized field in there in the beginning. A derivative acting on a field brings down a power of the momenta with I. All of these are squared. So these guys in particular that are acting on phi star will bring out the momenta square of the antiparticle. We'll have minus the momenta of, well, this, again, we have to symmetrize in here, the momenta of one of the antiparticle, let's say P2 squared. But it could also be the other one, no? In all of these combinatorics, that's what you're doing. It could also be minus P4 squared, and then there's the Hermitian conjugate that will bring P1 squared and P3 squared. Yeah, this is not a force. Sorry, I was talking about 5-4 theory and writing, but yeah, that's just 2 powers of the complex and the field. Or yeah, sorry about. Thanks for that. Thanks. Yeah, sorry, but for this there's an extra combinatorial factor. So let's think about the case in which we associate P2 in this operator with any one of the 5-star particles. Then the other one of the antiparticles and the other particles can come from either phi here or phi there. So there's an extra factor of 2 for these guys. Right? So once I've chosen, if you want to think about this that way, I've chosen phi star to be someone in particular, P2. Then who is phi and phi associated to P1 and P3? Well, it could be 2 combinations, that 1, 3 or 3, 1. Basically, there's an extra factor of 2 up front. And that's what we get there. Right? We've derived a Feynman rule. I know you're familiar with, I don't know, QED, Feynman rules, even lambda 5/4. And sometimes you're just given the Feynman rules and told to compute without thinking much, but you can also derive those Feynman rules yourself for any theory that you want. And this is the way you do things. Maybe you've done it earlier, I don't know. Righty, but all of these, for this scattering, all of these particles are on shell. In which case I can substitute all of those momenta for their mass squared. So now it's just a matter of counting. Minus I lambda, there's a factor of 2 up front, and 4 guys. So it will be a plus 8 CE times m squared over lambda squared. CE. And voila, the magic of the 2 theories being the same. We've gone through step by step. We have to know that lambda bar is related to the other couplings of the original theory in that way, but once we know that we go to an amplitude, we don't show particles, amplitudes are the same. Alrighty, this is an important point, so any questions about this, you can ask now. Well, yeah, so all of this, if you really want to be safe, you talk about probabilities, cross-sections, and in particular, we do know that, for example, infrared divergences only cancel in the square of amplitudes, considering cuts. So if you want to be safe, do compute cross-sections, probabilities, not just the amplitudes. So I can imagine there might be exceptions in that sense. The statement, the sort of the situation invariant statement is any physical quantity will be the same. And this level is good enough that the amplitude is the same. Very good. Any other question? We're going to do this over again, if I have time. Right, so this is how you follow the derivation, and this is somewhat clear to you. Maybe it is also quite a simple case for some of you, and it might be clear to see. And I haven't proven this in generality. I'm saying any physical observable. So let's push it a little further and go to 6 points and see if that still happens. It's going to be slightly less trivial. It's going to be trivial-ish for the S-bar theory. We look at it, and the 6 point, I'm going to focus on the local part, by the way. There's also the part with propagators coming from lambda 5/4, but I'm going to look at the local part of it. And in the case of the contact, in the case of S-bar theory, it's simple enough, somewhat simple enough. We have 6 fields in here. That will give us the contact piece. The rest will be with lambda, but those have propagators. So we derive the Feynman rule for that operator. Now there's quite a few more legs. In, out, in, out, in, out. You can put names on them if you want. We see in the S-bar theory. We go through the motions again. minus I lambda CE over lambda squared. I'm deriving the Feynman rule for this guy. It's cube. There's a factor of 2, blah, blah, up and down, lambda CE. That's all right. Now, all of these combinatorics is, again, I myself, when I was a student, find it quite hard to follow at the time. But can any of you see from where you stand what will be the combinatorial factor in front of this operator? Coming from, again, there's 3 incoming particles, 3 incoming antiparticles. I can associate it to any of the 3 phi stars and phi's in here. Yes, it will be a 3 factorial squared. You can put any of these 3 in any of those 3. What is the total possibilities for that? Well, 3 factorial. The first one with any of those 3, the second one with any of the 2 left over, and then just 1 left after that. Sorry, yeah, this 2 is, I should have written this somewhere else. We can look at this, the C6 coefficient at the end of the day is that, yeah. Alrighty, so that's going to be a 3 factorial squared. Now we look at the other theory. There's no contact 6 point in the action itself. If you look at it, there's only 4 fields in here, and the normalizable action only has lambda phi 4 in there. Lambda phi 4 itself, by itself, would only give us non-local terms, so we can focus simply on one insertion, and this is a bit lengthy, so let me put it somewhere else. Well, maybe I can fit it in here. For the other theory, we have, this might be produced by, oh, I'm sorry, I'm going to keep with this conventional throughout. Any higher dimensional operator insertion is going to have a box, a big box in it to distinguish it from renormalizable terms. So this has a box. In here, there's a box and not a box for this term. That term will have a box. Just to keep track of things. So in this other case, where there's no direct contact term in the action, but there will be in the amplitude, we have one insertion of the high dimensional operator and one insertion of lambda, which in S, we do call it lambda. Right, and again, you can give names, so I don't know. Well, I'm not going to put arrows quite in there because there's a number of possibilities. Let's do the combinatorics, which again, if that was, if this was easy for you, then maybe this is not so easy. If that was hard, I'm sorry, this is going to be a bit trickier. But again, hope you can follow. So now, you have to realize, so this is the way I think of it. You can also, by the way, just go in the literature, and there's papers that, not for the 3 level, but at level, they'll give you what is called the symmetry factors. But anyway, there's 2 possibilities the way I see it. So there's the higher dimensional at that guy. It could be that the arrow or the particle is coming in or out. So there's one possibility of it going that way, and another one of it going out. Right? And each of these, if let's see if I thought about it the right way. Sorry? There's going to be momenta flowing through this. But I haven't written the rest of it yet. I'm just doing the combinatorics so far. Yeah, no, it is, but I want to tell you why. So there's going to be, well, at the end of the external, so we can work out the external symmetry factors that will be the same. I will assign 3 to 3, that will be 3 cube squared yeah, sorry. Came back to me. Righty. So let's say we have 1, 2, 3, and this is coming in, going out, going in. Right. So the way one can think about this is, so I'm choosing one of the incoming arrow legs of this vertex to connect with the other one. How many I have to choose from? There's 2 incoming legs in there. Right? So that would be a factor of 2 in there, or which ones I choose from that side. Now, how many I can choose from the other side was actually the same. This is going to have, if that flows that way, and this flows in, out, in. Right, I also have 2 to choose from there, 2 times 2. And the same thing will be true for the arrow going the other way. 2 times 2. That is sort of the internal, if you want, that's the internal combinatoric. Now what I'm left with each of those, for each of those cases will be 3 incoming and 3 outgoing that I have to assign to the 3 incoming and outgoing external states. So again, I can, now you can put 1, 2, 3 in any of the, well, the notation incoming is odd, so 1, 2, sorry, 1, 3, 5. 1, 3, 5, and there's 3 factorial ways to associate those in there, and the same for the other antiparticles and particles. So that's, again, not easy to follow, but that is actually the right result once you put it in there. There's also, by the way, maybe I'll have time to sketch it, but I'll also given you how to do this with weak rotations, which is the way you do it. You just put those creation annihilation operators in the in state, 2 insertions of the action terms, and just commute away everything. So there's a brute force way of doing things, which is just put those creation annihilation operators and compute away. And if this was for you how to follow, it's at least good to do once all of these, scrambling of creation annihilation operators. But it's with Wick's theorem that counts those for you. Righty, but I've done that, and to do that, so all of those combinatorics will take care of assignments. Then I have the lambda insertion and the other operator that in this notation is minus I for lambda over 4. And for the other one would be, where do we have these guys? Something like, something like this. It will be minus ICE lambda squared and in this Feynman rule, I had already symmetrized in all of those possibilities. In here, I've done it externally, so I have to divide that by those combinations. That will be, long story short, minus, I pulled the minus out front, so 3 of those will be out of the external particles. So there's going to be 3m squared, and one of them is going to be one of the particles we exchange, q squared. But this will be over 2. Right, once I've sort of divided by 4 the full term in there, because 4 was the combinatorics that I got out of this, 2 times 2. I'm just divided by that. Again, there's a brute force way of doing this. You can go ahead and do it that way. There's also the propagator of the scalar in between. And now we can finally begin to see where things come from. So the contact term will be coming out of the cancellation of the fact that there's a q square on top and a q square in the denominator. So I can always add and subtract plus m squared minus m squared. right? And be left with, so in here I'm going to minus m squared and plus m squared. And if I do it explicitly and with all of these messy factors up front, so it's minus minus plus, but there's also two i's, so it'll be minus I 3 factorial squared lambda ce over capital lambda squared. And if I worked out all of those factors of 2 and 4, 4, 8, and 18 here as well, so that's what it is. The extra non-local term will look something like 8 m squared over q squared minus m squared minus I lambda halves of 3 factorial. But we don't care about this one, we just want to compare the local piece. And we've already extracted the local piece, there's no q squares in there. Alrighty, I know this was a tough path to follow, all of these combinatorics and stuff, and it's not something that, it's not one of those things that you can get right away looking at a blackboard, but it requires a bit of thinking. There's more details in the notes if you want to work this out. What we get is what we should get. That contact term, after all of this scrambling from combinatorial factors using on-shellness, is the same as the contact term we got in the S-bar theory. Okay, perhaps it's an overkill. So I showed it to you for the 4-point. Maybe that was enough. For higher points, it is also true. You just have to work a bit harder to prove it. But that's, I just wanted to show you the path. You follow it if you will. Righty. So let's bring it back together. What have we learned from all of this? If we now trust this result that physical predictions of both theories are going to be equivalent. Okay, so you can do this yourselves or trust me in that regard. What we've learned is that if we add that SE term in the action with this new operator that wasn't there originally in our EFT, so we add this to our original EFT action that we started with, we'll have now one more operator in there, and some might say, you have forgotten an operator in your basis. You're not as general as you claim to be. What we've seen, however, is that action can be translated with this field redefinition into an action that instead of that funny operator has this phi star phi cube operator that we had already in our basis. Right? And for that matter, what we're saying is that at order 1 over lambda squared, that is equivalent to the same SEFT theory we had, but with an extra contribution to the C6 coefficient. So C6 will be going to C6 with all of those terms that we now have worked out earlier, minus lambda C. We can incorporate that new operator into the old basis we had, just shifting the value of one of those coefficients. Right? This is the whole point about using equations of motion to reduce your basis. And I try to make it explicit. And then the last little bit of info for this is, well, I mean, what do I care if I call it C6? If I call an unknown plus another unknown, it just doesn't make no sense from the point of view of the EFT. I'll just call it C6 again and work with it. I don't care if it's all of that. What it is exactly, that value coefficient, is a problem of the UV, not of the EFT. So I can just call this again C6, C6 primes, C6 prime, whatever you want to call it, in the spirit of, again, we are, like I said, we're pretty unrigorous in physics at times calling things. This is one of the cases in which it's better to be unrigorous. It doesn't matter what you call it. It's just a coefficient, so leave it there. And you can be general enough. Right, so that has shown us that the basis we're using is in fact general enough to contain other operators in there. The actual way to work this out, to be sure that you're in the right full basis, is the whole topic of Joy Deep's lecture. So we're not going to dwell on this much more. But any questions before we move on? Yeah, so that's another thing. If you weren't quite convinced by this argument and all of those factorials, you can match the non-local terms in this other theory. You will also have the lambda 5 for lambda bar term in here. So you have a theory, another set of diagrams that do look like those ones, but with lambda bar. But lambda bar itself cyclically contains CE. So you could match those as well, if you want to be really, really sure. And this also, of course, the problem that was suggested already in team lectures of just take a trivial free theory, do a field transformation. Righty. Other questions? Yeah, so if you want at this level, this is a definition for me for convenience. So what we have in here is S4, or original renormalizable Lagrangian, plus a dimension 6 operator after I substitute in here my, well, this is in here. My equation of motion is a dimension 6 operator, but there's also a dimension 4 in here. And again, in the spirit of not introducing too many names for things, this, from the point of view of effective action, will be just added up with the 5-4 term that we already had in our theory. So might as well put the two things together and call it lambda bar. And that's what we're doing there. Yeah, sorry about this. There's a lot of names that I'm giving to things and this and that. It can be hard to follow at times. It's all in the spirit of keeping, keeping things neat and organized. Thank you. Any other questions? From the middle diagram, that one. For these two. Right, yeah, so I haven't drawn any arrows in this diagram. This is the way this looks like. But now I have to put in arrows to know what particles and antiparticles are doing. Now, if I think of this, these two are different vertices. So it makes sense to talk about, is the particle coming in or going out? Which is to say, is the arrow going that way or this way? Now, if I think of which arrows can come into that vertex, well, originally, if we look at the diagram here, there's two arrows coming in. And in the whole point of combinatorics is see how can I do this? Well, I can make that I can take this leg and be the one that connects to the lower vertex, right? So you think of it, I can take this arrow coming in and make that one the leg that connects to the lambda vertex. But I could just as well take this other leg that is also, that I said, coming in, so that one is also coming in, and take it to be the one that is connecting the two of them. There's two choices in there, but there's also two choices down here as to what other arrows you wheel them into, you connect them to. So that's why I have here a 2 times 2. Then the very same story repeats when the arrow is going in the opposite direction. I can take any of those 2 times any of those 2, so that will be another factor of 4. Now what we're left with, the leftover combinatorics, is what I call the external combinatorics. Which is to say, I've already decided who's connecting the two vertices, now I have to decide which labels I put on the outside legs. In the spirit of those, this we start with, so I'm going to call even all the incoming particles. And then you can see that if I have to assign 3 numbers to 3 legs, there's 3 factorial ways to do it. I can put I can put number 1 here, or number 1 there, or there. That's 3. After I assign number 1, number 3 has only 2 places to go. and number 5 has no, just one place, so 3 factorial. The same thing for antiparticle, we'll use a 3 factorial squared, 1 for each, particle and antiparticle. Any other question? Yeah. In fact, we'll have to use one thing that is, if we have time, we'll get to that. One thing that is true is that when you take this here to the loop level, you will a priori generate operators of the form you had, but also new operators. Like you might generate the very operator we're talking about, CE here, and then you have to convert that back onto your original basis. So this, as long as this procedure, which can be done and will be done if we have time, order by order in the loop expansion, that stays true. Yeah. Right, how much time left, Rick? Because this, I think this marked 55 minutes, but okay. Right, so just very quickly, a few words on unitarity, and also to connect it to some relevant, maybe not super relevant nowadays, but a relevant historical piece of physics. So really quick about unitarity. Unitarity is that conservation of probability that we already encounter for quantum mechanics. Remember the reflection and absorption, no, the reflection and transmission coefficient squared added up to 1 because probability is conserved. You can put that into the language of quantum field theory with an S matrix that I'm going to define as S of a wave going left and S of a wave incoming left and then outgoing left. That is the transmission coefficient, and S of a incoming wave and then reflected is the reflection coefficient. So I can rewrite that unitarity condition that I wrote before as S dagger S, where there's going to be an internal sum of those indices, and in here I can take what am I going to take? I put the dagger in there. It's dagger S of an incoming wave and an outgoing wave. So if you think of that in matrix term, you're going to sum over the intermediate indices, and you should obtain, one, the identity, which would also be in this notation R squared plus T squared. The same thing is true in the S matrix of QFT, only the intermediate states are not just two states, you're summing, in fact, integrating over a lot of states. So real quick, and this is again something that I don't have time for, so it's a problem for you guys to do later. But to be precise, if I define my S matrix for some 2 times 2 scattering and the identity, but let me do that identity explicit in this momentum space. I'm going to call this 2EP, 2EK to the 6th power, and 2 Dirac deltas for the 3 momenta. Prime. That is what we would call the identity piece. And by the way, this is an S matrix element for particle P coming in, an antiparticle K coming in, and then P prime and K prime coming out. The non-trivial piece of scattering is contained in what I call the envirometric element minus IM. But not I call, everybody calls that with a conservation of 4 momenta. Alrighty, so you can apply the same condition. SS dagger equals the identity. Now in this space, the identity is that funny combination of Dirac deltas. I'm going to write this schematically. It will look something like this. So S and S dagger. And what you have to sum over is the intermediate phase space. There will be phase space for these particles, Q space, Q prime, and you have to, well, keep different names. Well, as we had it, that's fine. And integrate over their phase spaces, Q for one and for the other, and for prime. There's more details in the notes. If you go through that exercise and you assume that the amplitude is angle independent, which is the simplest case in a partial wave expansion, you get the following bound on the real part of the amplitude. 2 to 2 scattering is smaller or equal than 8 pi. Righty? I'm skipping a whole lot of steps, but you might have seen this somewhere. But you can do it, and if you follow the notes. Now, real quick, applying this to our example, we have 4 points for these theories in there. One of them I just erased, but there's going to be 4 field terms in our expansion with 2 derivatives in them. So, long story short, I put them in this environmetric element. I do the same type of computations, and I will get that this MO scales like the center of mass energy S. That is what the 2 derivatives are going to turn into over lambda squared times whatever coefficient I have in there. So unitarity or conservation of probability will tell me that there's an upper bound on those coefficients. For the theory to make sense, unitarity is not something you can give up. But also, for all EFTs, it's not a constant, it's center mass energy over lambda squared. And that might be problematic. Can anyone see where or in which case that, what I'm saying, how could this inequality be violated? If you think of yourself as an experimentalist, you have a handle on the energy of your experiment, which way you will go to try and violate this relation that some theories told you is true. Yes, if you go ahead and just crank the volume up and take the energy higher and higher up, if you reach an energy of the order or lambda squared, the whole thing will break down. It's not that quantum mechanics and quantum field theory explodes or implodes, is that you need a UV completion for things to work out. But if you turn things around, this is the strongest argument we have for new physics. Whenever you find something like this, an amplitude that depends on center mass energy like that, you know that you manage to measure the coefficient in there, and it's a number, and that is the case, for example, of the Fermi theory, where we measure G Fermi. We know what that is a number, and if that's a number and this is 8 pi, we know where this will be violated. You put numbers in there, the energy of scales at which this will be violated is 246 gigaelectron volts, given that G Fermi depends on that scale. So G Fermi told us already 100 years ago that we need new physics at that scale. Now we know that that is the case, and even when Fermi theory was completed by the W discovery and the Z discovery, the same bound applied for Goldstone boson, or the longitudinal part of the W's. The scattering, who told us there was something else needed. And if you heard that the LHC was guaranteed a discovery, well, that's the reason why. That's the strongest reason we have, and that's why something was going to be found at LHC. What happened to come out was the Higgs. It could have been something else. But that's why I reference also in the notes to the classic paper by Quick, Tucker, and Lee, where they find more about that in there. But yeah, I'll leave it there. Sorry that I took a bit more than I should have. But any questions about any of this, I'll be happy to take. Yeah, so good point. So this in here, just like it happened for the Fermi theory, we measure only the combination at low energies of C and lambda square. So actually all of this splitting C, the coefficient into C and lambda square is artificial for the point of view of the EFT. It's just, you see the whole thing. In the case of the standard model, as we know that G Fermi is G squared over MW squared. So it's that combination. What this tells us, however, is sort of a stronger bound. It says that you cannot really go above 246 and not find anything. In practice, nature might be kind to us and say, well, actually, I'm going to let it happen before 246, and that's still fine. As it happens, sort of the completion of that was 80 giga electron volts for the W mass, and even for the Higgs, 125. So if you put in the numbers, in fact, if you put in the numbers in here, we're square root of pi and everything in there. Yeah, sorry, so there's something that I missed in there. If you put the numbers, it's going to be V, but there's also going to be a square root of A pi in there. Sorry. Just working it out. So in the paper by Lee, Tucker, et al., they put the numbers in there, and this came out to be 1 tera electron volt. You can just do that sort of square root of A pi for that. So we did know that the LHC was going to find something up to the scales of 1 TeV for sure. So that's the case. Exactly where, we don't know. But that's why it's an inequality. It has to be before then, at most at that scale, but for sure it can happen before. Other questions? So the constraint is non-perturbative. So in deriving this constraint for the S matrix, that part is non-perturbative. The point is that this, we have, the left-hand side, we have computed perturbative.